So, a very good afternoon to one and all. So, what I'm going to present here is for the week 6. Uh, for the week 6, I think, just let me, just 1 minute. Yeah, so welcome to all the students on this live interactive session for the week 6. So this was one of the video which was not been uploaded properly on the NPTEL SWAM portal, but as per the students request, so I'm uploading it again, and today we'll just go through some of the lecture contents which we have seen on that day. So this is just for your reference, and I've already uploaded the PDF and the PPT in the PDF format on the NPTEL SWAM portal, and you can download it from there. So I'm going to discuss the same thing here which we have solved during that day, as I have to upload this YouTube video for your future references. Okay, so we'll go through. So welcome to all the students on this live and tech session on chemical engineering thermodynamics course on NPTEL SWAM portal. Like I have been saying it from the last weeks that this course has been offered by Professor Gargi Das. She is a professor in the Department of Chemical Engineering at IIT Kharagpur. And a little bit about myself, that I am Rajput Shubham Ajukumar. I am a PMR scholar in the Department of Chemical Engineering at IIT Madras. Okay, so this is for the week 6, and the week contents are somewhat like this. So the first concept that we're going to discuss is the concept of fugacity and the fugacity coefficients and the fugacity of the condensed phase. So this week 6 is totally based on the concepts of fugacity, its fugacity coefficients and their estimation, along with the discussion on the condensed phase fugacity. Okay, so we'll move on right now. So first of all, we have gone through some of the concepts which are known as the molar properties and the partial molar properties. So the partial molar property has been described with a term which is known as mi bar, which is del N by del Ni at constant temperature, pressure, and the number of moles I that is not equal to J, which can be written in terms of the total molar property as del Mt by del Ni, temperature, pressure, number of moles of I not equal to J. And the solution, total solution property can be written as M of T is equal to summation of Ni mi bar. Now, if you see that in molar properties, there are another term which is known as the partial molar volume or the molar volume. So we have defined in molar volume as V is equal to x1 V1 bar plus x2 V bar and so on. So x1 V1 and x2 V2 and similarly x3 V3 will come out depending upon the number of components involved in the solution. So the partial molar volume can be written as V bar is equal to del Vt by del Ni. Similarly, at constant temperature, pressure and number of moles J not equal to I. Okay, so these are some of the concepts related to the partial molar properties, the partial molar volume and molar volume. Similarly, we have discussed how we can write the molar volume component 1 and component 2. So molar volume component 1, that is V1 bar, is equal to V minus x2 del U by del x2, and V2 bar is equal to V plus 1 minus x2 del U by del x1. So where x1 and x2 are none other than the mole fraction of the components 1 and 2. Similarly, chemical potential, how to say what is chemical potential. So if you see, mu I is a term which can be defined as a chemical potential. It can be written as Gi bar del Gt by del Ni at constant temperature, pressure and number of moles I not equal to J. So the total Gibbs free energy is a function of temperature, pressure and number of moles of the components involved. So in the differential form, if I write this equation, that is chemical potential mu I, it can be written as dgt at constant temperature and pressure. Differential function of total Gibbs free energy to constant temperature and pressure is summation of mu I dni. Okay, so this is the concept that has been discovered in the as a chemical potential. Now, if you see what is fugacity and fugacity coefficients, because this week has been related to the term fugacity and its relation with the fugacity coefficients. So we have like Gibbs free energy, differential of Gibbs free energy is equal to RT dln of F. Now we know that from the like routes like Pyi bar is equal to Pi bar by P, that is the with pressure or the saturation with pressure by the total pressure, and Y is the mole fraction in the vapor phase. So limit P tends to 0, as limit pressure tends to 0, F by P, that is fugacity to its pressure is 1. And the fugacity coefficient is none other than represented by the term the symbol phi. It is the fugacity to its pressure. It is known as fugacity coefficient. Now there are two different types of rules which I have discussed. The first is the Lewis-Rendell rule, and the second one is Henry's law. So the Lewis-Rendell rule is misstated by Fi bar is equal to Yi into Fi, where Fi is the fugacity of the component I, and Yi is the mole fraction of the component I in the vapor phase, and Fi bar is the fugacity of the component in the atom phase. Similarly, Henry's law is related to that of the liquid phase, that Fi bar is equal to Xi into Fi, where Xi is a mole fraction of component I in the liquid phase. Now, since we know that have been liquid and vapor phases involved, so I can write as the vapor pressure of the component I as xi pi s, where xi is a mole fraction component in the liquid phase and pi s is the vapor fraction of the component I. Okay. So I'll move on to some of the solving some of the numericals. So the first question says the relation du mu is equal to RT dlf is valid for any system or any component only at. Now we haven't given du mu is equal to RT dln of f. We have known that dg is equal to RT dln of f, and we know that phi, that is figurative coefficient, is equal to f by p. Now I have written, so this is valid at a constant temperature actually, like we have discussed in the previous terms. What is partial molar volume, Gibbs free energy, activity coefficient, and figurative coefficient. So the function, the relation d mu is equal to RT dn of f is valid at a constant temperature. So the correct answer will be A. So this is the simplest question just for the quick concept. Okay, so I have written and printed from the relation du is equal to RT dnf is valid for any system and any component only at a constant temperature. Okay, so I will move on to the next question. When a gas behaves ideally at low pressures, what is the approximate value of the Poynting correction factor? So this correction factor has been taken it to the consideration, which is known as exponential of Vc, that is at constant volume, Pc P minus P set by RT. So this is known as Poynting correction factor, which has been taken into consideration when gas behaves ideally at low pressure. So for an ideal gas, the consideration is that pressure should be low, and for the Poynting correction factor is given by exponential of Vc. So if this says the gas behaves ideally at low pressure, so pressure should be low. If you put pressure is low here, the if an exponential of that term will be 1. So that the final answer will be 1. Okay, because at ideal gas pressure will be very low as a consideration, as an assumption for that. Okay, so the correct answer is 1. So put the pressure 1 here and then solve this equation. The Poynting correction factor turns out to be 1. Okay. Now this question, the fugacity of a component in a mixture of ideal gas equal to. Now the fugacity in a mixture, like I've been discussing, if we say the number of components are 1 in the system, if we say number of components are 1, 2, 3 and I, where I is not equal to J. So the partial pressure of the components in a mixture is equal to the mole fraction of the components into the saturation vapor pressure of that components in the mixture. So it's been related by the partial pressure of the components in the mixture, say Pi. So Pi x1, P1, x2, P2, x3, P3 and so on. So it's related to the partial pressure of the components in the mixture. Okay, so this is also related to the concept we have discussed in the starting of the lecture. Okay, so the fugacity of the component in a mixture of an ideal gas equals to the partial pressure of the component in the mixture. Okay, we'll move on to next question now. So now this question is like determine the fugacity of methane at 350 Kelvin and 25 using a Lee-Kessler chart giving critical temperature and pressure and eccentric factor omega. Now we know that the fugacity coefficient given by the fugacity of the component to its pressure, and fugacity can be found out using the fugacity coefficient as this. We need to find out the fugacity. So given the temperature and pressure are given to us and critical temperature and critical pressure. Now we know that reduced temperature and reduced pressure formula, that is Tr equal to T by Tc and Pr equal to P by Pc. We can find out the value of Tr and Pr, and we can use this equation, which is phi equal to phi naught plus omega phi 1. So we take the logarithmic of both the values and you can find these values with the help of the Lee-Kessler chart. So now here you can see these are Lee-Kessler charts. We already have found the value of reduced temperature and we have found out the value of, this is the Tr value. So we have Tr and Pr. If you find out the Tr and Pr, you can find out both this value, log phi naught and log phi 1. So by finding out the values of log Tr and Pr, we find out the log value of phi 1, and similarly we will go Tr and Pr, we will find out the value of phi 0. That is both intersection, you go to the y-axis. Similarly here both intersection, Tr and Pr, and go to the y-axis. That corresponds to log 0 and log phi 1. So we have taken log 0 and log phi 1 from the Lee-Kessler chart using the value of Tr, Pr, and we have used this equation. We have given the omega value here. Directly put this value, you can find out the log value of phi. Now put this value of phi here, that is minus 0.0075. So you can find out the value of phi is 0.98. Okay, just a minute. Okay, so if you find out the value of phi, then what we'll do is that we will put the value of phi here, and we know the pressure value, that is 20 bars. So 0.99 into 20, this turns out to be the fugacity coefficient. So this is how we can find out one can find out the value of the fugacity using the fugacity coefficient, that is phi into p. And in order to find out the value of phi, if you have been given the Lee-Kessler charge, just find the value of reduced temperature and reduced pressure temperature, and using both the interaction, suppose reduced temperature is 0.5 and TR is 1, we'll go from here till state point 1 and then intersect here, so that will be log 5. And similarly here you have to go and check the TR value and the PR value. Okay, so this is like I've been saying, like we have to find out the value of critical temperature and the critical pressure. Now from the Lee-Kessler charts, like I've shown you how to find out the log phi naught and phi 1, just go find out where is TR pair value, go straight above, when it comes go intersection Y. Similarly, go straight above where it intersects, go intersect Y. Okay, and we have given eccentric factor. We use this formula, log of phi is to log phi naught plus log phi 1 into omega. All the values here, find out the value of phi, and since phi is equal to f by phi, that is fugacity coefficient, you have been asked to find out the fugacity f. So f equal to phi into p, fugacity coefficient is 0.9834 and pressure is 20 bar. So the correct answer is 19.67. Okay, so we'll move to next question quickly. Yeah, the parsimonial property of a component in a mixture is equal to, so this is what we have been discussed during the starting of the lecture, that is parsimonial property, mi bar. So the parsimonial property of a component in a mixture, so the total molar property will be summation of ni into mi bar, which indicates the component's contribution to the total property of the mixture, where ni corresponds to the number of the components I in the mixture, where ni is not equal to j. Okay, so the correct answer is this. So the parsimonial property of a component or mixture indicates the component's contribution to the total property of the mixture. And the reason being that is parsimonial property can be positive, negative, or zero. It is an intensive property and it varies with the composition of the mixture, because n is the number of components involved. So if I say n1, n2, n3, there will be n1, n1, n plus n2, m2 plus n3, m3. So it's related to the component's contribution to the total property of the mixture. Now this is another question: which among the following is not zero for an ideal solution? So now volume change of mixture, entropy change. Now the one thing, if you see the is not zero. So if you have gone through the concepts we have been discussing, like the entropy of the universe. So the entropy of the universe continuously goes on increasing, and it can be related with the equation which is known as del equal to det q by t, or ds equal to dq by t. Now if you take for an ideal solution, the entropy of the universe continuously goes on increasing. Okay, it has never been zero. Okay, so the entropy change of mixing is not zero because it goes on increasing. So the correct answer is C, that is entropy change of mixing is not zero for an ideal solution. Okay, so these are some of the concepts that I'm given. Please try to remember this, guys. So the property of an ideal solution, even if they ask different things, but you know what is an ideal solution. The properties are no volume change of mixing, no enthalpy change of mixing, no internal energy change of mixing, negative useful energy change of mixing, and positive entropy, because the entropy of the universe goes on increasing. So delta S is greater than zero, and the correct answer will be entropy change of mixing is not zero for an ideal solution. Okay, we'll quickly move on to the next question. So the Lewis-Randall rules. So now before starting the lecture, going to the numericals, we have discussed what are two different rules, that is Lewis-Randall and the Handles rule. So the Lewis-Randall rules holds well for any gas or mixture at low pressure, because we have been given like the fugacity of the component I in the mixture is the mole fraction of component I in the vapor phase into the fugacity of component I in that phase. So Fi bar is equal to Yi into Fi, which is valid for any gas mixture at low pressure. Okay, so please remember Lewis-Randall rule is valid for any gaseous mixture at low pressures. And the condition for that is physical properties of the component should be similar at low pressures when gas behave ideally. So an ideal gas is if you say the gas is ideal, you can say that only if the pressure is low, and at any pressure the component of the interest is in large excess. And the Lewis-Randall rule is very valid mostly for the gaseous mixture. For the liquid or the liquid mixtures, we can say it for a Henry's rule. Okay, so the Lewis-Randall rule is valid well for the gases at a low pressure, and that is behave as an ideal gas, and usually we usually use it for the gaseous mixture. For the liquid mixtures, we use the Henry's law. Now this is what the Henry's law constant, which is termed for the liquid. Now you can see there is an oxygen in water, that is for the liquid mixture, we can use the Henry's law. So the Henry's law constant, it is given by Ki at 298 is 4.4 into 10 to 4 bar. What is the solubility of oxygen in water in terms of mole fraction at 298 Kelvin for partial pressure of 0.25 bar? So we just use this equation, which is partial pressure of the component I is equal to Xi into Ki. We have been given temperature and the Henry's law constant and the partial pressure of the oxygen, that is 0.25 bar. So we get Xi is equal to Pi by Ki. Partial pressure of oxygen is 0.25, and the Henry's law constant Ki is 4.4 into 10 to 4. We can find out the mole fraction of the oxygen in water, it is xi is 5.6 into 10 to 6. So this is just simply how you can use the, or you can say, Henry's law concept for determining the mole fraction of component. Similarly, if they have given mole fraction and the partial pressure, we can find out the value of the Henry's law constant, that is Ki. Okay, so you can see this xi is going to be by Ki. You can find out the value. Just put the values of Henry's law constant 4.4 to 10 to 4, and the pressure is 0.25 here. Okay, we move on to next question now. So we have been given two components, n heptane and toluene forms an ideal solution. So at 373 Kelvin, that is 100 degrees Celsius, the vapor pressures are P1 and P2 are given to us. Determine the equilibrium composition of n heptane in the liquid and vapor phase at temperature of 370 C and capacity of this. Okay, so what we'll do is, starting the numerical, we will write component 1 as n heptane, component 2 as toluene, and the saturation vapor pressure is given to us as P1 as P2 as 106 and 74 kilopascal. Now we know that since they are in a mixture, we can say the total mole fraction is equal to 1, that is x1 plus x2 equal to 1, and similarly y1 plus y2 equal to 1. So what we'll do now, that the total pressure of the system is the component into the P1s and component into P2s. So this is a component contribution to the total system. So total pressure will be x1 P1s plus x2 P2s. We'll put all the values of x1. Since x1 and x2 is not known, what we'll do, we'll use x2 equal to 1 minus x1 here, and we'll put the value of P1s and P2s here. So directly what we'll do is that we'll directly put the values of P1 and P2 saturation, and put out the value of final value of PT. Now since we don't know the value of like P1 and P2, what we'll try to rearrange this equation, and we come out in the formula x equal to P minus P2s, P1 minus P2s. From this we can find out the value of mole fraction of component x1. If x1 is known, what we'll do, we'll put x1 here and find out the value of x2. Now in order to find out the vapor phase mole fraction, what we'll do is that we'll use the Raoult's law, which is yi is equal to xi into pi side by p. So we have taken for the component 1, that is y1 is equal to x1 p1 side by pt. So we'll put x1 as 0.8, p1 saturation as 106 kilopascal, and the total pressure as 100 kilopascal. So the y1 saturation, so the mole fraction of the component I in the vapor phase turns out to be 0.6. So this is the simplest one, just to use the value of total pressure. Pt is equal to x1 p1 set by x2 p2 set. Use x1 plus x2 equal to 1, because the total mole fraction has to be 1, that is 100%. So if x1 x2 is not given, we write x2 in terms of x1 and use this equation to find out the value of x1. Once x1 is known, use the Raoult's law, yi is equal to xi pi side by pt, and for the mole and for the component 1, use this equation, that is replacing I by 1, and find out the value of y1. Okay, so now we move on to the next question. So this is what I have been written in the numerical form. So Pt is equal to x1 p1 set plus x2 p2 set. We have written x2 in terms of x1. Find out the value of x1, that is p minus p2 saturation divided by p1 saturation minus p2 saturation, and y1 is using the Raoult's law, that is yi is equal to xi pi side by pt, and this is the total pressure. Okay, I have written here, because the total mole fraction has to be 1, as is 100%, that is 1. Okay, so the correct answer is 0.862 and 0.813. Okay, so now this question relates the two components. The vapor pressure of benzene, ethyl benzene can be related using the Antony equation, this and this. So now whenever you see this type of equations which relates, like ln of p set is equal to a minus b upon, this is a minus b upon t plus c. Similarly, ln of p2 set is equal to a minus b upon t plus c, where temperature here is given in degrees Celsius and the pressure is in kilopascal. Assume that they form an ideal solution. Calculate x1 and y1 at temperature of 25 degrees Celsius and pressure of 10 kilopascal. So what we will do is that, since temperature is 25 degrees Celsius and pressure is 10 hectopascal, we will use this Antony equation to find out the value of vapor pressure of component 1 and vapor pressure of component 2. What we have done here is, we have taken that equation directly from this guy, these two equations for the component 1 and component 2. Instead of temperature T, we have put it 25 degrees Celsius here directly, and find out the value of P1 and P2 set. Now, like the similar one, since the total pressure is x1 p1 set plus x2 p2 set, and the total mole fraction has to be come out to be 1, that is 100%, we'll find out the value of x1, that is p minus p2 set divided by p1 set minus p2 set. Put all the values, we can find out the value of x1. Now then what we'll do is that we'll use the the Raoult's law, that is yi is equal to xi into pi set by pt. We can find out the value of y1. So this question is similar to the previous one. The only thing is that we have not been given directly the saturation, vapor pressure of component 1 and 2. Instead, they have given the Antoine equation. So what you have to do is to put the value of temperature of 25 degrees Celsius here, find P1 set and P2 set, and all this remain the same. They're finding out the total pressure, find out the component mole fraction x1 in the liquid phase using the total pressure equation, and then using the Raoult's law to find out the mole fraction of the component 1 in the vapor phase, that is 5. Okay, we move on to the next question. So this is a similar question that I've been explaining here. Temperature T is 25 degrees Celsius and x, find out the value of P1 set and P set from here. Use x1, we'll use the total pressure equation. Pt is with x1 P1 set, x2 P2 set. Then x1 is to be rearranging this equation. We can, so x2, since we don't know x1 and x2, what we have done here is we replace x2 as 1 minus x1, because x1 plus x2 equal to 1, so x2 equal to 1 minus x1, and this entire equation can be written in terms of x1 as P minus total pressure minus P2 set divided by P1 set minus P2 set. Put all the values, find the value of x1. Now then what you have to do is to use this Raoult's law for the component 1, that is phi1 is equal to x1 P1 set divided by total pressure, find out the value of phi1. Okay, move on to the next question. So the following data is available for N-butane, the critical temperature, critical pressure, and the eccentric factor. Using the Lee-Casnell general correlation tables, the compressibility factor for N-butane at temperature of 340 Kelvin and pressure of 7.6 bar rounded to 2 digits after decimal is. So we need to find out the compressibility factor, that is Z. Okay, we have been given critical temperature 425.1 Kelvin, critical pressure 37.96 bar, and omega is 0.2. Now we know that eccentric factor Z and compressibility factor Z is given by Z equals Z0 plus omega Z1, when omega is given to us, eccentric factor is 0.2. Now we know that PC is given to us and TC. We know that reduced temperature and reduced temperature can be found out PR equal to P by PC and TR equal to T by TC. We have been given total pressure and total pressure, find out the value of reduced pressure and reduced temperature. Once reduced pressure and reduced temperature is found out, we'll use these values directly into the compressibility factor equation, that is Z equals Z0 plus omega Z1, and find out of the values here. Now Z0 and Z1 can be found out using the help of the generalized correlation tables of Lee-Casnell. So I'm using this TR and PR values, and I found out the values of Z0 and Z1. So we have put this Z0, Z1 values directly here, and we have found out the value of compressibility factor Z. So you have to see the Lee-Casnell correlation tables. In that tables, find out this value of PR and TR. We can find out the value of Z0 and Z1, and then use this equation Z equals Z0 plus omega Z1. Omega is given to us 0.2. Z0 and Z1 can be found out from the Lee-Casnell general correlation tables. Using the value of PR is 0.2 and TR is 0.8. Then you can find out the value of Z, compressibility factor, that is 0.8307. Okay, now this is another question. So this is similar one, but here you have to find out the residual Gibbs free energy. Now similarly, since the critical temperature, critical pressure, and eccentric factor omega is given to us, we'll find out reduced temperature, reduced pressure, and reduced temperature, that is PR equal to P by PC and TR equal to T by TC. Now since we know that the Gibbs free energy, that is G is equal to H minus TS, now we have been asked to find out the residual, that is residual Gibbs free energy GR is equal to HR minus TSR. Now we'll try to rearrange this equation and we'll find out in the terms of the eccentric factor, that is Z is equal to Z0 for omega Z1. Similarly, we have written like the residual Gibbs free energy in terms of eccentric factor terms. So the residual Gibbs free energy can be found out using this equation. So what you have to do is to find, using the Lee-Casnell general correlation tables, you have to find out all these values and put these values here just to calculate the answer. So this is simple one, just you have to know how to look at the Lee-Casnell generalized correlation table. Okay, so this is similar to the previous one, just the only thing is that we have been using to find out the residual Gibbs free energy. So this is what I have for the week 6, and thank you all the students for joining this live interactive sessions. If you have any issues related to the like week 6, please do let me know on the NPTEL Swim portal. We'll meet you next time for the week 7. Till then, thank you for joining this live interactive session for the week 6.